Hi everyone, it is Miss Nelson. We are back with day 3 of our Unit 8 unit of weather. And today our objective is what causes local and global winds? So, to start this lesson, I want you to imagine that you are sitting on a beach during a hot summer day. Sounds nice, right? So imagine you're sitting there and you feel a nice breeze. Which way is the wind blowing? Does it blow towards the ocean or does it blow towards the beach? It turns out that during a hot summer day, wind is almost always going to be blowing towards the beach or away from the ocean. Why is that? By the end of today, you should be able to answer that question. So the reason has a lot to do with specific heat. Specific heat is the amount of energy needed to change a substance 1 degree. For any of you who cook, you can think about it like this. To heat up water, you have to put it on the stovetop, right? Imagine you have a thermometer in the water. It's going to take a certain measurable amount of heat or energy to change that water 1 degree, say from 212 degrees to 213 degrees. Imagine you're also cooking some meat in the oven. You could also measure the amount of energy needed to change that meat 1 degree, say from 95 degrees to 96 degrees. That amount of energy is the specific heat, and it is going to be different for the water than for the meat. It turns out that every object has its own specific heat. And believe it or not, in our reference table, many of those objects are listed on page 1. So go ahead, go to page 1 of your reference table and find the chart that talks about the specific heat of common materials. If we look at that diagram, which of those materials has the highest specific heat? Liquid water. Liquid water has the highest specific heat. And what that means is that water is going to need more energy and thus more time to heat up or cool down. It's going to take a lot longer for water to heat up or cool down than other things like basalt or granite, like rocks, or metals like iron or copper. And it is this that causes local wind, like sea breezes or land breezes. So, first we're going to talk about sea breeze. A sea breeze is when land heats up faster, lowering the pressure, when air flows from the water to the land, and this happens during the day. Let me explain using this diagram. So, go ahead and label the diagram as I am explaining. So, during the day, when the sun is out, the land is going to heat up a lot faster than the water. That is because the land has a lower specific heat, so it doesn't take as much energy for it to heat up. The water with a much higher specific heat is going to take a lot longer to heat up. So the land is going to get hotter, and the water is going to be colder. We know from previous lessons that hotter temperatures means lower air pressure. And colder temperature means higher air pressure. You can think back to the hot air balloon example, or to when that man put balloons in liquid nitrogen. Hotter temperature means lower air pressure. Colder temperature, higher pressure. So we can label our diagram with the land having low pressure and the water having high air pressure. If you look at the diagram, you can see that where there's low pressure, the warm air is going to rise. And then the high pressure, the cold air sinks. We also know, though, that air is going to travel from high pressure to low pressure. Think back to the crowded subway going to the emptier subway. So air is going to travel from high pressure to low pressure, and it is that causes the sea breeze. This is the reason why during the hot summer day where we feel breezes coming from the ocean to the land. But what happens at night? At night, we have what's called a land breeze. A land breeze is when land cools down faster, increasing the pressure. The air flows from the land to the water, and this happens during the night. So again, if we look at our diagram, at nighttime, the land is going to cool down faster than the water. Again, this is because the land has a lower specific heat. So land can cool down faster, and this is going to leave the water hotter. It takes much longer for the water to change its temperature because it has a higher specific heat. Colder temperature means higher air pressure, and hotter temperatures means lower air pressure. So we can label the land with higher air pressure and the sea with low air pressure. Once again, we can see that over the land, that cold air is going to sink, and that over the water, the warm air is going to rise. Again, we also know that air will travel from high pressure to low pressure. So at night, if you were standing on the beach, you would feel the winds coming from the land and flowing towards the ocean. That is called a land breeze. But that's just what happens on a beach, or local winds. Local winds, as we know, were caused by differences in temperature between the land and the ocean, and that's what caused air to flow from one direction to another. But globally, we know that there are places that are hotter and there are places that are colder that are going to cause differences in air pressure. This unequal heating of the Earth's surface forms global winds. These winds are going to blow from a specific direction, and they're going to travel extremely long distances. If we look at a diagram, we know that at the equator, that is where we have warm air. And that warm air is going to rise and then move towards the poles. At the poles, we have cool air that sinks and moves towards the equator. So if we look at our diagram, the equator, that's where it's hot, right? Hot temperature means low air pressure. So if you follow that arrow, you can see that at that location, air rises from the surface of the Earth up. That hot air is going to rise and go up because it is low air pressure. At the North and South Pole, we have cold air. So that cold air sinks from the atmosphere down to the surface of the Earth. And we can see that is high pressure, high air pressure. So on the surface of the Earth, air goes from high pressure, where it's cold, to low pressure at the equator, where it's hot. We name wind based on the direction it comes from, not where it's going to. So, in this diagram, where would New York be? So if you look in this diagram, when the air comes from the west, we call it westerlies. When the air comes from the east, we call it easterlies. Where would New York be? There is New York. Go ahead and put New York on your diagram in your notes. So, New York is between 30 degrees and 60 degrees north, so we experience westerlies. That means we experience wind that comes from the west. And if we look at a diagram, we can see that in the United States, and thus in New York, wind and weather will travel from the west to the east. So there's the west, there's the east, and we can see that the wind is flowing from west to east, or what we call westerly winds. For this reason, throughout the week when I'm calling my parents in Chicago, I'll often call them and ask them, how's the weather there? And because I know that in a couple days that wind and weather is going to travel from their location in the west over to us in New York in the east. And it'll travel, the wind will travel from west to east, also a little bit north. And we're going to get that same weather in New York in a few days. All right, global winds we can see on page 14 of our Earth Science reference table. So go ahead, flip to page 14 of your reference table. And if we look at this diagram, we can see that arrows show the air movement between specific latitudes. So those arrows represent winds that are traveling long distances across the Earth. Go ahead and look at the diagram and see if you can label where there will be high and low pressure based off of those arrows. You have about 1 minute and 30 seconds to see if you can label the diagram. I'm going to check back in once the timer has gone off. All right, let's see. So if you labeled the diagram correctly, you're going to label high pressure where I've highlighted in blue and low pressure where I have highlighted the diagram in red. How do you know where to label this diagram? Well, there's a few ways. So first, we know that wind will always travel from high pressure to low pressure on the surface. So the lines with the arrows should always start at the high pressure and head towards the low pressure. We also know that air is going to sink in high pressure systems and rise in low pressure systems. So if we look at these locations where air is sinking in the high pressure system, we can see it's going from the air sinking down towards the earth. In low pressure system, the air rises away from the surface of the earth. Lastly, if we remember, wet air is actually not as heavy as dry air. So, where it's wet, we're going to have low air pressure because that air is not as heavy. And where it's dry, we're going to have high air pressure because that air is heavier. If you haven't labeled your diagram, go ahead and label it now. But if we look at these arrows, we can see that they curve. Why do the winds curve? Why don't they just go straight from high pressure to low pressure? And the reason has to do with the Coriolis effect. So, the Coriolis effect is caused by the rotation of the Earth on its axis. And it is responsible for curving the path of air and ocean currents across the Earth. What do I mean? Take a look at this red ball. It travels straight down this white line. However, because the Earth is spinning or rotating underneath, that ball appears to take a curved path. It is the same with our wind currents. So, in reality, wind is going straight, but because the Earth rotates underneath it, that path appears to curve. Depending on where the wind is, it will appear to curve in a different direction. So, if the wind is in the northern hemisphere, that is north of the equator, the path will appear to curve to the right. So if I stand here and I'm walking straight, I would curve to the right. Winds in the southern hemisphere will appear to curve to the left. So imagine you start at the right here at the equator, and you're walking south. If you're walking south along this path, facing quote, quote, down, but facing south, your path, you'll go little by little, you'll walk more and more to the left. You're going to curve to the left. And surface or ocean currents are mostly determined by wind. So the wind is going to brush along the water of the ocean and carry the water with it. But if we look at these two diagrams, this of the wind currents on the left and the diagram on the right of the ocean currents, both of which are in your reference table, we can see that though there are similarities, for example, the wind that travels here, these southeast winds, is similar to the ocean currents here, they are not exactly the same. Why is that? That is because land masses block or deflect their direction. So, wind currents carry the ocean water with it, but because there's land in between that block it, they are not exactly the same. All right, that is your notes for today. I hope you enjoyed. Your exit ticket, please send me a picture of your notes on Remind. This helps me track who is actually watching these videos and who's not, because I need to make sure that everyone is continuing on with classes, even in the midst of the coronavirus. Also, please remember to go to Castle Learning and begin your mock regions, your assignment. Soon, I'm going to be posting a Castle Learning assignment having to do with Unit 8, and that is going to go into your third quarter grade. So make sure both the mock regions and the assignment that's coming up for your Unit 8 weather are completed on Castle Learning, as well as you sending me pictures each day of your notes, because that will be your participation grade for the third quarter marking period. All right, I hope you guys are staying safe and healthy, and I'll check back in tomorrow. See you. Bye.